Hi. Stars form out of gas, and gas is detected using H1 observations at radio wavelengths. In this video, we'll talk about these 21 centimeter radio observations, the correlation between dust and gas in galaxies, and try to unravel the importance of H1 data in understanding the evolution of galaxies and the history of star formation in the universe. Let's begin. Unlike the rest of electromagnetic waves, radio emission is a consequence of a change in spin of the lone electron in a hydrogen atom. These are referred to as the up and down spins, meaning that the electron and proton spins can be either parallel or antiparallel. The relative orientation of the spins affect the magnetic force between the electron and a proton. The state with the spins parallel have slightly more energy than the state with the spins antiparallel to each other. The atom can undergo transitions between these two states. The energy difference between these two states corresponds to a frequency of 1420 MHz or a wavelength of 21 centimeter. The energy of the transition divided by the Boltzmann constant, that is the quantity h nu by k, gives the temperature which is necessary to see collisional excitation of the hydrogen's upper state. This comes out to be around 0.07 Kelvin, which means that even at the low temperature of the interstellar space, there will be sufficient energy to excite transitions between these two states of the hydrogen atom. The 21 centimeter line is therefore easily observable under interstellar conditions. While the possibility of such a line of hydrogen was first discussed in 1940s by Henk van der Hulst in Netherlands, the first detection of the 21 centimeter line from the interstellar hydrogen was made in the early 1950s by a group of researchers at Harvard led by Edwin Purcell, who later won the Nobel Prize in Physics for his work. The 21 centimeter signal is easily detected by a radio telescope because these long wavelength rays are not blocked by the Earth's atmosphere. But note that this is a hyperfine transition which occurs once in 100 million years for a particular atom, which means that it takes an atom that long to move from one energy state to the other. But yet, we are able to detect atomic hydrogen using this transition because of the abundance of hydrogen in the universe. So even though the time scale for an atom is very long, there are plenty of transitions happening all the time because there are so many hydrogen atoms around us, which makes the 21 centimeter line a very useful tool for detecting and measuring the abundance of hydrogen in the universe in general and in specific celestial objects. The 21 centimeter line can be observed in emission or absorption. For the line to be in absorption, there must be a background continuum source whose brightness temperature at 21 centimeters is greater than the excitation temperature of the atoms in the cloud which is being observed. Under most conditions, the excitation temperature of the 21 centimeter line is close to the kinetic temperature of the gas cloud. By studying both absorption and emission lines in a given region, it is possible to deduce the excitation temperature and the optical depth of the gas therein. The excitation temperature therefore allows us to calculate the kinetic temperature of the gas, while the optical depth can be converted to column density for atomic hydrogen. So if we know the column density and size of the cloud, we can also find the average local density of hydrogen. So basically, astronomers can use the 21 centimeter line observations as an important tool for studying the physical conditions in the interstellar clouds. An important feature of the radio observations is that interstellar dust is transparent at radio wavelengths. Therefore, we can use the radio telescopes to detect objects across the galaxy far beyond what we can see optically in the presence of dust. Since we can use it to observe clouds anywhere in the galaxy, the 21 centimeter line is an extremely useful tool for studying the structure of the galaxy. Also, since it is a spectral line, we can observe its Doppler shift and learn about the motions of these gas clouds throughout our own galaxy, the Milky Way. Although H1, that is atomic hydrogen, is quite abundant, the rarity of 21 centimeter emission or absorption from individual atoms means that the center of this line remains optically thin over large interstellar distances. Optically thin basically means that the H1 flux can be detected from objects far away because the radio light can pass through without much scattering and absorption. Now, assuming that the line profile is a Gaussian profile, the optical depth of the center of the line is given by the formula mentioned here. Note that since the line width is primarily due to the Doppler effect, delta V is expressed in units of velocity rather than in wavelength units. Typically, this delta V, which is the full width of the line at half maximum, is around 10 kilometers per second. The NH mentioned in the formula is the column density of atomic hydrogen, while capital T is the temperature of the gas measured in kelvins. For optically thin 21 centimeter hydrogen line, the optical depth is proportional to the neutral hydrogen column density. Studies of diffuse H1 clouds indicate temperatures of 30 to 80 Kelvin, a number density in the range of 100 to 800 million per cubic meter, and masses of up to 100 solar masses. This implies that in order to estimate the hydrogen column density, all we need to do is measure the temperature and 21 centimeter line for the gas in an object. It has also been found that for extinction of up to 1 magnitude in the V band, the column density of H1 is proportional to the column density of dust, suggesting that dust and H1 are distributed together in the interstellar medium. However, when this extinction A of V is greater than 1, this correlation breaks down, which means that the column density of H1 no longer increases as rapidly as the column density of dust. This further suggests that other physical processes become important when the dust becomes optically thick. Optically thick dust clouds shield hydrogen from sources of ultraviolet radiation. A consequence of this shielding is that molecular hydrogen can exist without undergoing dissociation by absorbing ultraviolet photons. Dust also enhances the formation of molecular hydrogen beyond what would be expected by random collisions of hydrogen atoms. This enhancement occurs because of two reasons. First, a dust grain can provide a site on the surface of the grain where the hydrogen atoms can meet rather than requiring chance encounters in the low-density interstellar medium. Secondly, the dust grains provide a sink for the binding energy that must be liberated if a stable molecule of hydrogen is to be formed. This liberated energy goes into heating the dust grain and therefore rejecting the hydrogen molecule from the formation site. If the column density of atomic hydrogen is sufficiently high, that is, of the order of 10 to the power 25 per meter square, it can also shield molecular hydrogen from ultraviolet photodissociation. This is the reason why molecular hydrogen clouds are always found surrounded by shells of H1. It is noteworthy, however, that stars form in clouds of molecular hydrogen, which is very hard to detect. The structure of hydrogen molecule is very different from atomic hydrogen. Molecules do not emit 21 centimeter radiation. Molecular hydrogen also does not have any emission or absorption line in the visible or radio wavebands, making it very difficult to trace it. But in some special situations, when the temperature of the gas is greater than 2000 Kelvin, it is possible to detect rotational and vibrational bands associated with the molecular bond. That said, astronomers often use other molecules as tracers of molecular hydrogen by making the assumption that their abundance is proportional to the abundance of molecular hydrogen. Amongst these, the most commonly used tracer is the carbon monoxide molecule CO, which is 1 part in 10,000 times as abundant as molecular hydrogen itself. But these observations are very difficult because the shift in the energy levels is often smaller than the width of the 21 centimeter line. But it can still be done because opposite polarizations are shifted in opposite directions. So astronomers subtract one polarization's spectrum from the other, leaving a very small but significant signal. Some of these experiments have successfully measured magnetic field of the order of tens of microgauss. Measurement of these magnetic fields have led to a pretty accurate picture of the structure of the cloud in the interstellar gas. These maps show an irregular cloud structure similar to that observed for the dust clouds, once again confirming that dust and gas coexist in the interstellar medium. Stars form out of gas, so it is not surprising to see a correlation between star formation rate per unit area per unit time and hydrogen gas per unit area present in a galaxy. In their seminal paper published in 2008, Piguel et al. Showed that the two quantities are almost linearly correlated. The scatter in their data suggested that the efficiency of gas converting into stars in a galaxy is determined by the conditions such as density and metallicity of gas locally in a cloud rather than the global properties of the galaxy itself. And evidence of this can be found in the fact that the H1 size of galaxies is often much larger than their optical disk. For instance, our neighbor M83 looks like a perfectly circular face-on spiral in this optical infrared composite image, but its gigantic gaseous disk is revealed in the H1 observations. Similarly, the merging galaxy pair in the M51 system narrates a very different story in the optical and the H1 view. Now, we know that star formation peaked around 10 billion years ago in galaxies and has been declining since then. This could be due to several reasons. First, the galaxies which formed stars vigorously 10 billion years ago have now lost most of their gas and are mostly evolving passively. Secondly, supernovae explosions from massive stars which formed back then threw out the gas from galaxies, once again causing a decline in fuel for star formation in galaxies, that is, the cold gas. It is also possible that the expansion of the universe itself has moved the galaxies so far away from each other that they are not gravitationally interacting as often as they were when the universe was younger and smaller in size. Since these interactions are also an important trigger for causing bursts of star formation, the expansion of the universe could have led to a decline in star formation. So to summarize, the study of gas in galaxies near and far is crucial in identifying various processes responsible for a universal decline in star formation in galaxies. I really hope you learned something new today. If you like our videos, please do follow and subscribe to our channel and share our content with other astronomy enthusiasts. Do let us know what other topics would you like us to cover in this space. We really look forward to your suggestions. I'll see you next week. Until then, take care.